Okay, hello everyone. Module 9 address resolution, ARP, with the protocol at the end. So I think we're almost halfway through CCNA 1, Introduction to Networks, and we're dealing with layers of the OSI model. We started with the physical, we went to the data link, we touched on the Ethernet, which is part of the data link in the physical layer, one of the most important technology in those two layers. Then we touched on the network layer. Then here we are, Taba address resolution. It's not a layer of the OSI, but it's a very important protocol which allows us to, how do I put this? Link, which allows us to resolve IP addresses so that we get MAC addresses. We resolve logical addresses so that we get the physical addresses, right? So address resolution is a fundamental concept which explains how devices translate logical addresses, which is our IP, into physical addresses. And when we talk about physical addresses, it's obviously the MAC address. So address resolution helps us translate logical IP addresses to MAC addresses. And understanding this is very essential, especially in troubleshooting of network connectivity issues. If a device can't resolve an IP address to a MAC address, it means it cannot communicate. So some of the problems that we have, let's say you have a PC that is not connecting to the internet or connecting to other PCs in a local area network, it might be an issue where the AR protocol is not functioning well or not even present, right? So address resolution protocols can also be targets of attacks. So for example, we're going to look at where you have a device that is acting as if it is a legitimate device in a network. And when ARP is in action, instead of resolving with the correct device, you resolve with the illegitimate device, and that is a problem. That is how hackers can get access to the network. So the study of ARP basically helps in understanding how do you stop against such attacks. So I think we'll basically look at how the translation takes place. Then we'll look at the security side of it. Because if it can be used to attack a network, then we need to secure against those type of attacks. We need to protect our network. So that is basically what we're going to be doing. And I think this is a very this is a very short session. I think one video, less than 20 minutes will be enough. Right, let's go. So our objectives, our major objective is to explain how ARP and ND, neighbor discovery, enable communication on a network. We're going to compare the roles of the MAC address and the IP address, describe the purpose of the ARP, and describe the operation of IPv6 neighbor discovery. So with IPv4, I think with the network layer, we introduced two protocols that are used in layer 3, the IP protocol and the IPv6. With the IP protocol only having a limited number of IP addresses, Arupera, by the way, 32 bits. And we said 2 to the power of 32, that's the maximum number of addresses that we can have. IPv6, another way of addressing 128 bits. That's the only difference. The other one, a representation, one is hexadecimal, one is decimal. So with those two types of protocols that we also have two types of protocols that are used to resolve from the IP to the MAC. So with the IP version 4, we have ARP, which is used for that. And with the IP version 6, we have this that they call neighbor discovery. But the function is, I think it's basically the same thing. Right, MAC and IP. There are two types of addresses that are assigned to a device with the physical, the MAC address, logical, the IP address. The MAC is used for NIC to NIC communications on the same Ethernet network. Very important, on the same Ethernet network. When it's remote, we can no longer communicate NIC to NIC via layer 2, the layer 2 physical address. With the layer 3, it is used to send the packet from the source to the destination. Whether local or not local, we can still do that. Layer 2 addresses are used to deliver frames from one NIC to another NIC on the same network. If the destination IP is on the same network, the destination MAC will be that of the destination device. I think we touched on this a little bit. So in this example, we have, this is a local network. There is no router there, no layer 2, no layer 3 device. So this is a layer 2 device. If you only see a layer 2 device, then that means that is a local area network. Right? So in this case, if I'm sending a destination MAC, so in this case, we are sending information. This is our transmitter, this is our receiver, right? This is part of the data. Let's say this is the frame. This is the frame that we have from this end. And from the frame, we can see it's part of the frame and the packet. We can see the destination MAC, which is the MAC address of this. We can see the source MAC, which is the MAC address of that. We can also see the source and the destination IP. So basically what we are saying here, if we have a local area network, the destination MAC will be the MAC address of the destination device. So this is the destination MAC. This is the destination of the receiving device. It's the same. But in a case where we now have a router, in my head, it sounds repetitive, but I hope someone who is learning and missed some of these points, they can always manage to understand where we're coming from through these repetitions. Right, so now let's say we have a router, and let's say we have another network. Let's get it right here. And we have another network, and we have PCs 3 and 4. These PCs are now remote to PC 1 and 2. So if PC 1 wants to send information to PC 2, here we are not going to have the MAC address of this device. If PC 1 wants to send to PC 3 in a remote network, this destination MAC is not going to be the same as that of device 3. This destination MAC will be the same as the IP default gateway. I think we got past that. Then this one de-encapsulates, re-encapsulates. Then from this point, we have the source and the destination here. Where ARP comes is usually from this point to communicate with this, because what we only know of remote networks is the layer 3 IP addresses. So what we only know of PC3 from PC1, what we only know is, most of the times, unless it has already been resolved, what we only know is the IP address. But to send a frame, you need the physical address, you need the MAC address. We cannot escape that. So that is where IP to MAC, IP MAC address is being resolved. That is where they come from, and that is where the ARP protocol is very much needed. Right. When the destination IP is on the remote network, the destination MAC address is that of the default gateway. We'll pass through that. ARP is used by IPv4 to associate IPv4 addresses. Then with IPv6, we have this protocol being used. That protocol, ICMP version 6, is being used to associate the IPv6 address of a device with the MAC address of the device. So this is a set of it's just a set of messages which we'll talk about later. We have no neighbor solicitation, NS, neighbor advertisement. Then another common one, router solicitation and router advertisement. We'll talk about those messages. They're just part of this ICMP version 6 protocol. Right? With this one, like I'm saying, we have NS and NA. With this one, we have ARP. And the whole process of exchange of these messages, that is what we call neighbor discovery. So neighbor discovery is based on ICMP version 6. And like I said in module 3, when you hear protocols, what I want you to see is exchange of messages. That's what I want to see. When you hear a protocol, ICMP version 6 is a protocol. So there are messages being exchanged. ARP, a protocol, messages being exchanged. Every protocol that you see, when you hear the word protocol, always think of messages being exchanged. And I think it becomes much easier to understand how the protocol will function because you're already wired. They are supposed to be some messages being exchanged. So I also wanted to put in, it's very important to know right? Okay. It's also very important to know this protocol. So we have ICMP. Then we have ICMP version 6. So this one is used for the version 4, ICMP. And this is where the ping messages, for example, the ping that you know which is used to test for connectivity, it is based on these messages being sent. So a message is sent, a request, an echo request, then you get an echo reply, then it means you have connectivity. If you send an echo and you don't get a response, that means you don't have connectivity. So everything is based on the protocol, which is just an exchange of messages. So I just needed to introduce that. All right, so the example we gave of connecting to a remote network. So here I think we have PC 1 and 2 communicating, PC1, PC2. The source mark is the same as here, but the destination is no longer the same as this one. The destination is still 555555, but here the destination mark is B. Why? Because it takes the MAC address of the default gateway. Then from there, the process goes de-encapsulation, re-encapsulation, de-encapsulation, re-encapsulation, until we get to this point. Now our packet is here. If our packets get here, what it only knows is the IP address, the destination IP. Then we'll need to resolve to get this MAC address. How we resolve that is basically what ARP is and what we discuss. So a device uses ARP to determine the destination MAC of a local device when it knows its IPv4 address. So if we know the IP address, then we can resolve what the MAC address of a device with that. What is the MAC address of a device with that IP? And ARP provides two basic functions for that: resolving the IPv4 address to MAC addresses and maintaining an ARP table of IPv4 to MAC address mappings. When we talk of this table, every table, in fact, we talked about the MAC I always say MAC addressing. Okay, MAC table, MAC addressing table. We talked about the routing table, right? This one contains MAC addresses and incoming port numbers. MAC addresses and incoming port numbers. If a switch wants to forward, it looks at that table. I have this MAC address. What is the port? If it doesn't find the MAC address, then the process of learning broadcasting takes over. But if the address is there, then we can easily forward to that specific address. So when we want to forward from a switch, we first look at the MAC addressing table so that we get a picture of the whole map of the network that we have, right? With the routing table, another map of routes. Now we're at layer 3. So there's layer 3, this is layer 2. Routing table, another map of routes where we want to forward our packets. Then we have the ARP table, another map again. It maps for every IP address that is known. There is a MAC. So if, I think I said at some point, if the IP is already resolved, then there is no need for the ARP process. What does it mean when we say it's already resolved? It means there is an entry in the ARP table of that IP address. So if we get to our router, we get to this point where we want to send to another network, where usually ARP takes over. And at this point, we look at the ARP table and we see the IP address is there and the MAC address is there. Then there is no need of going through the whole ARP process of broadcasting and trying to find the MAC address. We can just take what we have in the ARP table. So the ARP table is very important. For every IP address resolved, it is entered in the ARP table. Right. ARP functions to send a frame. A device will search its ARP table for a destination IPv4 address and a corresponding MAC. If the packet's destination is on the same network, the device will search the ARP table for the destination IPv4. If the destination IP is on different networks, the device will search the ARP table for the IP of the default gateway. If the device locates the IP address, its corresponding MAC is used as the destination MAC address. If there is no ARP entry found, then the device sends an ARP request. So if we do not have an entry, so we do not have an IP mapped with its MAC, then it means we need to send an ARP request, which is a broadcast, sent to all devices. Basically a message saying, I have this IP address. Who does it belong to? Then the device that has that IP address, it responds with its MAC address. And that's how we get to map. Then when it responds, the entry is entered in the ARP table and we have this. Next time when you want to communicate, we don't have to send this ARP request again. We just look in the table and voila, we have our mapping. Entries, removing entries from an ARP table. Entries in the ARP table are not permanent and are removed when the cache timer expires after a specified period of time. The duration of the cache timer differs depending on the operating system. ARP tables can be removed manually by the administrator. All right. It's very important to understand if we have an ARP table, it means it is being stored somewhere. It means it is taking up some space memory of the device, the switch, the router, whatever it is, right? Some memory space is being taken by that table. Now imagine a very huge network. You have thousands of IP addresses. It will mean 1,000 entries. How much space will you need to be able to store all those mappings? It will be a lot. So what happens is an entry, if you get an entry after a second, after a certain time, that entry is removed, and we get new ones. New one, the last one is removed, new one, the last one is removed, and it goes like that. The reason why is because we don't have any finite space on our devices. And that space is very much required, especially to process all the traffic that we have. So we don't have that much space to keep the ARP table. We have the MAC addressing table. It also needs this space. We have the routing table. It also needs this space. We discussed quite a number of more tables, quite a number of more variables that will need space to be stored in. So that's the reason why we can remove entries, which can be done automatically or manually by an administrator. Right. Typical question. Depending on the operating system, I've seen a lot of questions coming with, provided we have the Windows operating system, what is the time? What is the time that an entry is stored on the ARP table? It's just 15 to 45 seconds. To us, yeah, I think way. But to our devices, that's a lot of time. A lot can happen in 10 to 45 seconds. All right. Let's move. ARP tables on networking devices. I think you can try that on your PC. If you want to see the IP address and mappings of the MAC addresses on your PC, you can type in ARP-A. Let me see if I can do that. So you can see mine as well. It's ARP-A. Voila. So we have our IP addresses and the physical addresses. Very important to note this first address with FFFF, that's a broadcast. So if I want to send a broadcast to the network that I'm in, this is the IP address, which is the broadcast IP. And here we have the broadcast MAC address. Okay. Right. Let's move. ARP issues. ARP broadcasting and spoofing. ARP requests are received and processed by every device on the local network. Excessive ARP broadcast can cause some reduction in performance. Replies can be spoofed by a threat actor to perform ARP poisoning attack. Enterprise level switches include mitigation techniques to protect against ARP. Right. I think we hadn't discussed how an ARP request is sent, but it's very important now understanding how that is done. So let's say, for example, network antenna panel. Right. So if this PCA wants to communicate, or let me use an existing network that we've done already, so that we get to understand how ARP, right, let's use this one, how an ARP request is sent. Right, so if this PC1 wants to communicate with PC number 2, what basically happens is we'll need to communicate with the default gateway because we are communicating with the remote destination. Right, so this PC, we send a frame to the default gateway. But since it only knows the IP address of the default gateway, an ARP request will need to be sent, provided we don't have anything in the ARP table. That ARP request basically is a broadcast. So a broadcast from the switch here is very much simple. But if we have some PCs here, let's say we have PC 4 and 5, it means a broadcast will be sent to this PC and this PC and to the default gateway. I have this IP address. Who does it belong to? Then this default gateway will respond. These ones will be dropped. This one will respond with the MAC address. Then after responding, the switch will then re-encapsulate the frame. Now it has the destination MAC. With the destination MAC, that's how we get to this router. Then from this router, we get to this point. It's the same device. Then we want to get to this point again. Another ARP request is sent. This one responds. Then re-encapsulation takes place. The frame is encapsulated with the MAC. Destination MAC is that one. We get to this point. The same thing, a broadcast is sent, meaning if we had multiple PCs here, 7 and 8, from this point to the switch, a frame is sent to the switch with the ARP request, then the switch broadcasts. This one drops, and only this one responds. And when this one responds, that's how we get the destination MAC, and the frame is sent to PC number 2 via the switch. Now, so as I'm explaining this is how attacks happen. So let's say, for example, device number 8 disguises itself as the one which has, let's put the destination MAC here is 10 1 1 10 10 1 1 10. Right. Let's say device number 8 disguises itself as 10.1.1.10. And so this is a legitimate, is this correct? I think so. Legitimate. This one is in threat actor, attacker, let's just say attack. So this one disguises itself as the one with this IP address. So when an ARP request is sent, it's a broadcast. It means it is sent to this one, and to this one. This one declines because it doesn't have that IP address. This one responds. This one also responds. Let's say this one responds and it gets to this side. It means when this frame wants to be sent, it won't be sent here. It will be sent to the attacker. That's how attacks happen. So an attacker disguises themselves as the one with the destination IP. Then when the ARP process starts taking place, the request being sent, this one responds. And when this one responds, the frame is sent to the device that responds. So understanding ARP, the process when the requests are made, when the broadcasts are made, it leads us to understanding the security issues with ARP broadcasting. So as you can see, there we have our attacker. Where was our information going? I think our information was going here probably. No, our information was going to the gateway, right? Our information wanted to go to the gateway, but this one acted as the gateway. It just disguises itself with the IP address of this gateway. Then what that means, it means every time this device wants to communicate with the gateway, it will communicate with this device. And if there is sensitive information, that's a problem. A very huge problem. Right. AR spoofing. So in an ARP poisoning attack, an attacker sends forged ARP replies, falsely associating an IP address with the attacker's MAC address. That defines what we call spoofing. So we have the poisoning, that leads to what we call spoofing. Those are just the technical terms. But I think if you understand basically what is happening, an attacker is there, disguises itself as the default gateway, then it means packets are sent to the attacker instead of the default gateway. Right. Let's now look at IPv6. So with IPv4, we have ARP. With IPv6, we have Neighbor Discovery Protocol, which provides the address resolution, router discovery, redirection services. What helps with what basically happens, the exchange of messages that we have for address resolution, we have the neighbor solicitation and the neighbor advertisement. So in a network, let's put a router. So this is our PC. If this PC has an IP, the default gateway has an IP, we know the source MAC here, but we don't know the destination MAC here. How does it resolve? This is IPv6. So a message is sent from 1 to the router. That message is called the neighbor solicitation. If this one receives the neighbor solicitation, it responds with the neighbor advertisement. And within the neighbor advertisement, that's where you have information about the MAC address of the device. And basically, that's it. Then another function, I think this is not about address resolution. It's just a function of the neighbor discovery protocol, router discovery. In a network, how do routers know there is another router in the network? How do they know? There's an exchange of messages which is done, router solicitation, router advertisement. If a router receives the router solicitation, it responds with a router advertisement. And the router advertisement basically contains all the details about the router, the router ID, the prefixes that the routers are using. It is also the same way how devices get IPv6 addresses. In IPv4, we have DHCP. In IPv6, we also have DHCP, but there is something we call SLAAC. And it makes use of these types of messages, exchange of these messages. A device sends an RS, the router responds with an RA. I think we'll deal with RS and RA later. But what is just important to understand at this point, how are IPv6 MAC addresses resolved? There is an exchange of the neighbor solicitation. To solicit is to, I think is to ask, to solicit. So you ask, I have this IP address, I need some information. Then the router responds with the advertisement. Right, less than 1 minute. I think join with the next session.